So we may start the next lecture, and in the beginning I will finish the computation which I started already the last lecture, and it is the trying to find Killing vectors for ERS. Yes, that generalization of Minkowski space where eta ij is R minus R by R matrix unit here, and minus S times S matrix here on the right hand side. Yes, so this is eta ij for general ERS space, and our aim is to find the solution of Killing equations psi k g I j k plus psi k I g k j plus psi k j g I k equals to 0. These are Killing equations in general, and now our Gij is this one. So in particular, when we will be successful in solution of this equation, general solution, in particular we will find standard Euclidean space. This as a special case where S is 0. So we are going now to generalize from E2. We did E2 in particular, yes? E2 already done. You remember that we found that in E2, in standard Euclidean plane, there are 3 Killing vectors. One of them produces rotation about the origin, and the 2 other produce translation at the x direction and y direction. And in general, it is some combination of general translation and general rotation. Yes? Do remember that from the last time, that E2 is already solved explicitly because it is very easy. But now we want to solve first E3, and even ERS, it can be done quite easily. Yes. By the way, it is a exercise. I think that it is 4, 6, 10. Have a look, but it seems to me. And in principle, it can be done on exercises, on recitations, but it is so important that I prefer to do it myself here. Yes, because if it is not perfectly done in recitations, that I think that some very important knowledge is not given. So let's do it here in detail. So if this Gij is eta ij, which is constant, of course, then first this goes away because they are derivatives of G. And second, if this is eta kj, which is constant, it can come under the sign of partial derivative. So we can write it as psi k eta kj, and derivative with respect to I. This is nothing but psi j. It is lowering of indices because psi is a vector field. Yes, so it is tensor. It can be one can lower indices. So this second term altogether is psi j comma I. Of course, the third will be then similar way, psi I comma j. So our Killing equations are now psi I comma j plus psi j comma I equals 0 for all ij from 1 to r plus s. So this is the system of equations to be solved. And notice that actually we directly try to solve or to find covectors, not vectors, not killing vectors, but covectors which are where psi I is eta I j psi j, and of course then psi I is eta I j psi j. Yes, so after solving this equation, if you want the real killing vector, you have to raise index on this object which you solve from this, which you find from this equation. So how to solve this equation? There are several cheap tricks to do it. One of them is make a second derivative with respect to some k. So I j k plus j I k is 0. It is simple consequence of the original equation. Yes. And notice what this equation says, or what we can do with this equation. That it says that this object, the first object, is skew symmetric with respect to ij. Yes. Of course, it is the statement that the first object is anti-symmetric with respect to ij. This says the equation. And then what the equation doesn't say, but it is clear that here are second partial derivatives. So it is symmetric. This expression is symmetric in jk, and this expression is symmetric in ik, because there are several second partial derivatives, and you know that the order of doing partial derivatives is not important. So we have also that jk is plus psi I kj whenever we need to use it. So this is from equation, and this is commutation of partial derivatives. It is not from the equation, it is independent knowledge from the first year of analysis. And combining these two wisdoms, we can show that the first term is 0 and the second term is 0 independently. Yes. So let's do the computation. First, I will put it 1, 2. So from 1, it is minus psi I j minus j I k. Yes, from 1. From 2, it is minus j k I. I k k I. Now, again, 1, it is plus, because 2 minuses, it's plus, psi k, kj now, kji, which is from 2 again, plus psi k ij, and again 1, it is minus psi I kj, again 2, it is minus psi I jk. Yes. So by interchanging 1, 2, 1, 2, 1, 2 several times, we came to important conclusion that this expression equals minus the same expression. which means that this expression is 0. Yes? Now, it is very simple fact that what does it mean that this expression is 0? That psi a after second derivative of arbitrary type, arbitrary jk, is already 0, so it is a linear function, nothing more. Psi I equals linear in X. This is the only solution of the fact that the second derivative is 0. But it means also that also psi with upper index I is linear in X because it is just a constant difference. Yes. So what does it mean explicitly? That psi I as a function of X is some matrix which is constant plus some column. These are constant matrices. One of them is a square matrix, this capital A, and one of them is a column matrix, the small a. So this is the most general expression that psi is linear in X's. But now we obtained this equation with arbitrary a from not directly the original equation, but from this equation. Yes? And this equation is not equivalent to this equation. It is consequence of the first equation. So we have to put this either here or to the original expression, for example, or original equation, to obtain some knowledge whether these parameters of the solution are arbitrary or they are somehow to be specified more. Yes? They are arbitrary for this equation, but we don't know whether they are arbitrary for this or the original. So let's put it to the original equation here. So if psi I is this, what is psi I j? Can you tell me that from this expression, what is psi I j? Psi I comma j. If you do on this comma k, say, what do you obtain? This is constant, so this is 0. And comma j from this is what? This matrix, yes? So this constant matrix, where it is here. So if we put it back to the original equation, so the first term is vanishing, and the second, it is aki, and g is eta kj, plus here is kj, a kj, eta ik is 0. Yes. So the matrix A, capital A, is to be restricted by this equation. It is not arbitrary. Now what is it? It is a matrix product of eta A j I plus, and here is again eta A ij, yes, ij equals 0, yes? So this is the only restriction for the pair capital A and small a. Small a is arbitrary and capital A is not arbitrary. It is given by this restriction. Now, this restriction we already know. It is matrix equation that eta here is the same expression but transposed. Yes, this is ji, here is ij. So it is an equation that transposed plus original is 0. And if you remember, when we studied Lie algebras, this says that this capital A is from Lie algebra of SO, and these two numbers are S. If you don't remember, have a look. For example, if eta is just unit matrix, so when we study Euclidean case, there is no eta, and what is the equation? That A is antisymmetric. Yes, but if you have RS type of E, so with pluses and minuses, not directly A is antisymmetric, but some combination eta A is to be skew symmetric matrix. Yes. So if you don't remember, have a look. Yes, but because it is very important. So we now have a full solution that this is psi A. That means what is psi itself? It is psi A and the basis. So it is Aij J nabla A plus AI derivative with respect to I. Yes, here is the full solution. And as we see, it is parameterized by two objects. It is psi with this choice of arbitrary parameters. So there are many psi's. Yes, for each A, capital A and small a, we have one solution. And this is from SORS, and this is arbitrary, or what is also arbitrary, but it is from Rn, we can say, yes? And by the way, R plus S is N. Here. So we have n-dimensional matrices. This SO matrix is divided to RS, pluses and minuses, but altogether the sum is N. And here we have a column constant vector from R. Now, what we want to do, and when we want to understand this solution, yes, always after some final end of the computation, you have to try to understand what you get. So what we get here, it is first, we know that this is translation. That if you write, of course, a possible solution is 0A and A0, special cases. Yes. So if you because zero matrix is also from SORS, it is skew symmetric. So what does psi 0A? It is just this term, and we already studied it. And we know that it is a translation in the direction of AI. So the more interesting case is what is this part? So we will do some manipulation which shows it more clearly than from that. And which will give us the expression which is often found in textbooks or scientific papers. It is also a cheap trick, so we want to understand this part, psi A0 is A I J X J derivative with respect to I. This can be written as AX I. Yes. Now we know that eta A transposed plus eta A is 0. So A is from SORS. So we can compute that it is A transposed, eta transposed, which is eta is symmetric matrix, equals to minus eta A, or AT is minus eta A eta. So this is just rewritten this expression, nothing more. Now, what about A eta matrix? Eta and A are of the same dimension, square matrices, so they can be multiplied for both sides. What is in components of this A eta A? It is ij eta I k a k j. If we multiply it from the right, it has upper indices, which is I k eta k j. So there are actually two etas. One of them is with lower indices and upper indices. But it is the same matrix. Yes, the inverse to eta is again eta. So when we compute this, it is what? It is eta transposed, which is eta, and A transposed. The A transposed is from here. So it is minus eta, eta, A, eta, but this is unit matrix. So it is minus A eta. So what we see that also A eta is antisymmetric matrix. Yes. So this is minus A eta J I. This is also antisymmetric matrix. This is minus eta A J I. So eta A is antisymmetric and A eta is antisymmetric. One of them has lower indices, the other one has upper indices. Now what we can do is such a strange step that we will write this as A eta, eta x I. So what it is in components, it is A eta I k eta k j x j all together. And this we will call xk. It is not lowering of indices because x is not a tensor. It is just a notation. Now, what does it mean? Xk, which is plus or minus this xk because of the shape of the matrix. This eta matrix is diagonal, and you have there pluses or minuses. So this expression, if you have a look how eta acts, it is just plus or minus of the normal xk. Yes, but it is very practical to use it, because now have a look how this can be written. So again, psi A0 is A I j x j derivative with respect to I, which is at the same time I eta I j x j, check, derivative with respect to I. I put just this index up and this index down, yes, which is done here. Just put two etas inside. And now why this is important? Because this is a general skew symmetric matrix. General skew symmetric matrix. If A is any matrix from SORS, this is any antisymmetric matrix. So you remember from theoretical mechanics, the cheap trick, that if you have something which is skew symmetric and something which is general, then from the general you can just put outside antisymmetric part and it is still the same. Yes? The formula that antisymmetric Ij and general Ij equals antisymmetric Ij and 1/2 of general Ij minus general Ja. This trick, yes, that which we call some, not A because it is here, some A tilde Ij. So this is antisymmetric part of this general Ij object. Trick. We use it here. How? That we put minus xi derivative with respect to j and 1/2. And why? Why it is interesting? Because then we see that this is a basis of this part of Killing vectors. For each I and each j, these vector fields are Killings, and altogether all of them are bases, because this is just that arbitrary constants with basis. As usual, we find that what is the basis. So because it is general or arbitrary skew symmetric matrix, then doing skew symmetry part of this expression is exactly the basis of Killings, of this part of Killings. Of course, there is this translation part, which the basis from translation parts is this. And what we find, what we try to find is the basis of the rest of Killings. And here we see it. If we forget to do the antisymmetrization and then say that this is the basis, it will be not true. This is Killing only in combination with antisymmetric matrix. Yes? So the real Killing is antisymmetric part of this. Think it over. Yes? That you cannot say that this is Killing. Yes? Because only the combination of this with antisymmetric matrix works, is a Killing. But this already is a Killing because antisymmetric with arbitrary antisymmetric matrix means that these are Killings. Think it over. It is very important. Now, let's call that minus m, or yes, minus mij. So again, let's call mij equal xi derivative j minus xj derivative I, and let's call pi, just for this moment, this. Yes? So then, in terms of those vector fields, we can write the solution, the complete solution of a general Killing that is maybe minus with this convention. I think that minus, but check eta a eta ij mij plus ai Pi. So this is the complete and useful way how to write the complete solution, the general solution of our Killing equations. So first we see that there are arbitrary constants here and here, and there is a basis here and here. Because it is written in this way, we can directly see that where are arbitrary constants and what does it mean that where is a basis. Because it is a linear space of solutions. Yes? So it is the general linear combination of bases, and the basis is this and this for all possible ij, but notice that it is minus mji. So how many solutions we have? First, one matrix of vector fields. Here is 1, 2, and 1 n, and so on. Here is what? N minus 1 n. So here is the first part of vector fields, antisymmetric matrix of some vector fields, called usually Mij. And then we have vector fields of which can be written in this way. So how many vector fields are here? We know that it is n times n minus 1 over 2, and how many are there? It is n. So altogether, it is this. And what is it? It is just n times n plus 1 over 2. Why? Because you can put these n pieces here, and it is just the bigger matrix, including diagonal. And we know that this is the number of the elements of matrix, including the 1/2, and the diagonal is this number. And just 1/2 without diagonal is this number. So we see that this is the dimension of the space of solutions. Yes, it is the dimension of the space of solutions of Lie derivative of this equation for this unknown for Gij equals eta ij. So for ERS. This is the dimension of the space. And maybe remember that I introduced this number as the highest number, how many independent Killing vectors are possible in general on n-dimensional manifold. So we see that this manifold is interesting from this point of view, that it has the maximum number of Killings possible in principle. So it is very symmetric manifold. There is a lot of symmetries of this metric tensor. The maximum number of possible symmetries for given dimension. Now we understand what do these translations, and now we want to understand what do these Mij vector fields. So we'll solve the equations that for what they generate, that for the flow. And we just show it from one concrete pair of numbers. For each pair of ij, there is some Mij, and you can find what it does. And then the general solution combines all that. It is something similar, like we studied what do the triple of solutions, what does the triple of solutions for E2, Euclidean plane, and we find that there are two translations, one rotation, and the general solution produces some combination of translation and rotations, which is complicated in general, but the parts of the translation x, translation in the direction y, and rotation at our origin, we understand these three pieces, and we understand that, well, maybe the combination of them can be a bit involved, but we understand that from what it is composed. So we now want to understand from what the general solution here is composed, and for that we want to understand Mij. Why not Y2? It is not limitation. For Ij it is the same. So what is Mij? It is by definition xi x1 derivative 2 minus x2 derivative 1. And what is x1? It is eta 1 x1 derivative with respect to 2 minus eta 2 x2 derivative with respect to 1. So this is our vector field. Now what about integral curves? 1 dot is and 2 dot. 1 dot is given by this. It is minus eta 2 x2, and here 2 dot is here, so it is eta 1 x1. So we are to solve this set of equations. And now remember that these two etas which are here are just plus 1 or minus 1, no other possibilities. So we have altogether 4 possibilities, that x1 dot is plus x2 and x2 dot is plus x1. Yes, possibilities. x1 dot is x1, x2 dot is x2. The second possibility, x1 dot and x2 dot is, say, minus, here is, sorry, 2 and here is 1, sorry, it is important. So it is minus x2 and plus x1 and so on. Together, 4 possibilities. Yes. So the 4 possibilities naturally divide that you have the same thing, the same sign, plus plus or minus minus, or reversed. One is plus, one is minus. Then we know already what the equation do with different signs. So we already know that, for example, x1 dot is x2 and x2 dot is minus x1, that it is rotation. By the way, check that if you have minus here and plus here, it is perhaps the rotation to opposite side, but still the rotation. Yes? So, for example, maybe this. I'm not sure, but check. We already had this vector field because we had it like with xy notation. Yes, that it is rotation around z-axis in E3. So we know this. Now the new thing is what happens if we have 2 pluses. So this is the most important novelty. That what about this solution, these equations, what they describe? So it can be, this set of equations can be solved in the same way like with minus sign, that make dot of the set, second dot of 1 is x2 1 dot, x2 1 dot is plus x1, and the same second dot, it is 1 dot and 1 dot is x2. Yes, so we see that second dot of x1 is x1 and second dot of x2 is x2, and you you can write the solution either in terms of exponential. Yes, it is e2 plus t and e2 minus t, or, which is better, with sine and cosine hyperbolic. So for example, here, x1 as a function of t is some k1 cosine hyperbolic of t plus k2 sine hyperbolic of t, and the same for 2 with other two constants. Then you put it back, because here you have 4 constants, and the original set of equations needs only 2 arbitrary constants. So it is not possible that the 4 constants are arbitrary, but you will know what is the relation in the set of these 4 constants, putting this, of course, with x2 back to the set, and you will discover that if you write it in this way, you will have nice formula. Like that. So what is it? It is very similar to this rotation case, where you have 1 minus here, but because you have plus here, there are no cosine and sine trigonometrical functions, but exponential functions, or this cosine hyperbolic cosine and sine. This is important change. And what is it? It is called hyperbolic rotation of the plane. And what is the analog of this picture? This is standard rotation of the plane. Hyperbolic rotation, you should check it. Maybe I will put it, this number of exercise, this 4, 6, 10, which I did here completely. Maybe still it is okay for somebody to show us what this is exactly. Yes, so to show that the flow looks like that. So it is more complicated in a way, like the rotation. This is the reason why this is called hyperbolic rotation, because these curves are hyperbolas. So for example, this M12 with 2 pluses here is what? It is x2 derivative with respect to 1 plus x1 derivative with respect to 2, yes? This is the case for, this is the explicit vector field for this case. Now, how it looks, this vector field, for example, here. 1, x1 here, and x2. Here, x2 is 0. So this guy is not here. x1 is some positive number. So it is some positive number times derivative with respect to 2. Derivative with respect to 2 is here. So we see that really it goes like, perhaps like that, because this is the vector. Here the vector is here the vector is here, and here the vector is here. You can check easily. Then you can, for example, try to understand what the vector looks at this axis, these 4 points, and you will see that it is here, 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 and here. So directly on this on these 2 axes, it goes along this axis. This goes away from the origin, and this goes to the origin. So it is quite useful to play with this in detail and to understand it as much as possible. So this is the novelty of this RS case. That what is the complete result? that we have translations, we have rotations, and we have hyperbolic rotations. Yes, so this is the complete story, that three types of transformations which are different. Translations of the whole space, then you have rotations, and when we have rotations, if there is a minus between these two, either here or here, if you have minus, you have a rotation. If you have both pluses or both minuses, the same signs, then it is hyperbolic rotation. Notice that in these higher dimensional spaces, rotations are not around an axis, but they are in some two-dimensional plane. What does it mean? That, for example, here we have that xi as a function of t is this complicated thing from here, yes, from here. But what about x3 and xn? It is nothing. It is x3 at 0 and xn at 0. Yes? This vector field has this flow. Something interesting happens in the plane 1, 2, and nothing interesting happens here in the rest of the space. So the rotation or hyperbolic rotation is just in a two-dimensional plane, not in the whole space. This is the elementary rotation or elementary hyperbolic rotation. And the complete transformation is combination of these, which is, of course, then rather involved. So if I will put to the offer for the recitations this number, it just means that show us how this picture works. Yes, that solve this equation in detail and show us that what does it mean hyperbolic rotation in detail. Yes, not the rest. The rest was already done. That to understand the basic solution, that what about this vector field? Why it is important now? What it means physically, that Euclidean space of 1, 3 is Minkowski space-time. Yes, so our eta is 1, minus 1, minus 1, minus 1, and zeros. And what we found for this particular case, that there are 10, 6 plus 4 Killing vectors. These are translations. 6 is 3 plus 3. 3 are rotations, and 3 are hyperbolic rotations. Why this 4 is clear? Because it is 4-dimensional. Why 6, 3 plus 3? Because now whether it will be rotation or hyperbolic rotation is given that which pair of dimensions you take. If it is 1, 2, it is here plus, here minus. Check that you will have two pluses or 2 minuses. It doesn't depend. So in which pairs you have rotations? This, and this. 3 cases. When you have hyperbolic rotation, the first one with the second, first with the third, and for the fourth. Yes, there are 3 possibilities for hyperbolic and 3 possibilities for just rotations. So we see this. And now, what is physically this hyperbolic rotation? It is something which is in special relativity called boost. For example, in the plane x1, x2, here is ct and x. If you write down this formula for 0, 1, you will obtain directly so-called boost in the x dimension. What is boost? It is transformation. What should be done with x and t coordinates in special relativity when the observer goes with velocity v in the x direction. Yes, so we have x direction velocity v0, 0. And the question is how time coordinate and x coordinate transforms, not in the Galilean way, but in the way starting from Einstein, Minkowski, and Poincaré and those guys. Yes, the special relativity transformation of t primed, x primed, 3 dots boost. And by the way, nothing with y, nothing with z. It is pure boost in the x direction, which is something like that. Yes, that nothing interesting happens in the rest of coordinates, and very interesting things happens in a pair of coordinates. So, because boost is, of course, extremely important in physics, and it is shown that boost is just a hyperbolic rotation from mathematical point of view, that our analysis showed that if you find Killing vectors and then the corresponding flows for this case, you obtain the complete symmetry, which is usually called Poincaré symmetry of physics. Poincaré symmetry consists of combination of translation, rotation of your space, and hyperbolic rotation of your space-time, which are boosts. So we see that we obtained all transformations which are important for special relativity of going to other reference frame. You can change your reference frame just by rotation or translation, or going to reference frame which is going uniformly in some direction. And then the transformation is nothing but hyperbolic rotation in appropriate pair of coordinates. So it is an intimate connection with our results of finding Killing vectors of Minkowski space with important physics. That's why it is extremely important for physicists to understand this connection. Okay, now I go for something which is called conformal transformations. It is a slight generalization of isometry. Imagine that we have two vectors, some v and u, and as we know, two vectors, any vector can be understood through some curves. So imagine that we have two curves which produce these two vectors. So here is some gamma 1, gamma 2, and this vector is gamma 1 dot, and this vector is gamma 2 dot. And now we want to make some f, m to m, this is on some m, which changes this to f gamma 1 and f gamma 2. So this is now, we did it for in the length of the curve and this isometries and so on, this is f push forward of gamma 1 dot, and this is f push forward of gamma 2 dot. Here is our f. So if we have a diffeomorphism, M to M, and some two curves with some generating vectors, then the curves are mapped to other curves, and their generating vectors are, from definition of push forward, transformed to these new vectors. Now, we studied a situation like that for just one vector and for computing of length. Yes, because when you draw a picture with just gamma 1 and f gamma 1, it is useful for computing the length of this curve. But now we want to do something else, that here is some angle alpha, and cosine alpha, by definition, is what? It is g of gamma 1 dot gamma 2 dot over g gamma 1 dot gamma 1 dot squared, and the same g gamma 2 dot gamma 2 dot. We know this formula, it is just scalar product of these two vectors. What the scalar product v dot w is v w and cosine alpha between them. So from this formula, the angle can be defined in general in this way. And now the question is, if here was some angle alpha, here is some angle alpha primed. And what is it? Cosine of alpha primed by the same formula is g on f push forward gamma 1 dot push forward gamma 2 dot over g push forward gamma 1 dot push forward gamma 1 dot square root, and the same with 2. And now we can shift these push forwards to pullbacks of G. So it is F star of G pullback on original vectors. Gamma 1 dot, gamma 1 dot, and F star of G on gamma 2 dot, gamma 2 dot. Square root, important. So this is the formula that here is the original angle and here is the new angle between these new curves. And we can ask that what the property of F is needed, that these two angles are the same. That what is necessary to preserve angles. We already know what is necessary in order to preserve lengths of curves. Yes. So lengths of curves we need this property, which is isometry. And we studied it in detail locally, that Killing equations are nothing that to find these Fs, the flow of this F. Yes. And now angle between some gamma 1 and gamma 2, if they cross, of course. We can have a look from this formula that how we can choose this G to F star G in order that this equals to this. Yes. Notice that if we use isometry condition, here should be G, 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 and this is the same expression like here. So the first result is that for isometries, also the angles are preserved. Yes, this is a consequence. If you preserve lengths of curves, you automatically preserve angles between any two vectors. But it turns out that you can do something more. Namely, if you change, if this expression is not G, but it is some sigma G with sigma positive function, then it also works. Notice here that here you will have, instead of G, you will have sigma G. Here you have also sigma, but it is under square root, so it comes out as square root of sigma. And here again square root of sigma, and because sigma over square root of sigma and square root of sigma is 1, then you see that, that for this expression you can allow for more general change of G. That the pull-back G is not necessarily directly G, but some multiple of G. And this type of transformation is called conformal transformations of Mg. So conformal transformations are such diffeomorphisms which in this sense preserve G, not in the very detail like for isometries, but for in this sense more general. Now they form a group, you can check it easily. So if F1 star G is some sigma 1 G and F2 star G is some sigma 2 G, then you can check that the composition in any order, for example this, is some sigma, you can check or compute, and it is some sigma 3 of G. You can compute sigma 3 out of this input data. And of course, identity transformation is conformal because it clearly preserves angles, and inverse, if it is diffeomorphism, you can invert it, and inverse is also conformal transformation. So we have a group of conformal transformations of Mg. Now we see that isometries are special cases for conformal transformations. So it is a subgroup of isometries. Subgroup of this is the group of isometries. And by the way, there is something between them. It is so-called homotheties, where this is a constant function. You can check that if you have two F1, F2 with constant sigma 1 and constant sigma 2. This combination is also with constant, so there is a subgroup which is bigger than isometries but smaller than general conformal transformations. They are called homotheties. And then the full conformal transformation group is with, this is a function, yes? But positive function. How to find them, this conformal transformation? We can find conformal transformations similar to these killings by infinitesimal method, exactly like we did it for isometries, that we will try to find directly flows of conformal transformations. What does it mean? That here we will have sigma, which depend on t. So it is a function of x parametrically with respect to t. So this is an equation that we have flow of conformal transformations because for each t we have some function here. Yes? Now, if we compute d over dt at 0, exactly like for isometries, we obtain Lie derivative here with respect to some psi to be specified. And what is here? D over dt is d sigma x t over dt at 0. G has no t. And what is this? This is some function psi, already without t. Psi on m. Yes, because we did d over dt at 0, so t evaporates, just x remains. And again, this is a function. So we come to conclusion that in order to find conformal transformations, we have to solve more general equation than Killing equations, which is called Conformal Killing equation. They are more complicated and more general. In these equations, the unknowns are conformal Killing vector, so-called. It is this vector field, and also this is unknown. You do not know what chi is. Any chi which is smooth is okay. So you try solutions such that if you compute Lie derivative with respect to g, you just obtain just some multiple of g. And this multiple is unknown function also. Now you remember that Killing vectors, that means Killing vectors are solutions with 0 here, yes, special case. So conformal Killings contain Killing vectors as sub-Lie algebra. You can check that conformal Killings give you a Lie algebra of conformal Killing, yes, because the complete story give you a group, so this gives you Lie algebra. You can check, like here for the group, the algebra of conformal Killings. Now, its sub-algebra is of isometries of Killings. So Lie algebra of conformal Killings is typically bigger, higher dimensional. It contains Killing Lie algebra, but there are some other vector fields possibly. And it is typically finite dimensional, but not always, as we see, as we will see in a moment. There are some exceptions. But typically it is finite dimensional, bigger than the Killing. For Killing algebra, we have some restriction that n times n plus 1 over 2. So conformal killing is typically bigger. But there is an interesting and important exception from this rule. We will see it. But first, some examples. There are some exercises here. I will put them to recitations. What are examples mentioned? It was somewhere here. For example, there is exercise, well, with some number, 4, 6, 22, perhaps. If I have no this, because there is some number of some lower exercise, which is 4, 1, 5, I have no here, but I think that 4, 1, 5 is important for this, and I think that it is exercise which says that in I3 you have a vector field which produces this flow ITR. It is a flow. So the idea of 415 is the check that this is a flow, and compute its generator, what vector field generates this flow. And this vector field is R derivative with respect to R in coordinates R, theta, phi. So in spherical coordinates, it is this vector field. In Cartesian coordinates, it is this expression. So you can check that if you try to find integral curves for this or this vector field, you will obtain this flow. Yes? And now the question is this an isometry? I mean G in E3, yes, here. So you know how G in E3 looks like. You see some vector field. So if it should be an isometry, this flow will preserve length. Yes? But what this flow does actually, just from x1, x2 position, it goes in this way, always. And it changes R to this, which is bigger, because this at time 0 is 1, and then it is bigger. So it goes R to more than R, 10 times R, and 100 times R, and so on. So if you have some curve like here, this curve will be like that in a moment. Yes? And of course, this is shorter than this. So we see that it couldn't be isometry. But you can check that it is a conformal transformation, that it preserves angles. That if you have any two curves here, and some angles, here the image of these two curves give you other two curves with the same angle. Maybe it can be also visible from this picture, but it can be easily computed. For example, from this, what should we compute, by the way? It is Lie derivative of this vector field applied on dr dr plus r squared d theta plus sine squared theta d phi. Here is the end. So this is G in spherical polar coordinates. Then compute this expression. It is a must for you to be able to compute it quickly because it is very, very easy. If you don't know how to compute it just now, sit down at home and speculate that it is very easy computation from the properties of Lie derivative, not from some component formula. You have a properties that LV applied on tensor product, on sum, and so on. Yes, so, and after all, you will need to know what is, for example, this. And what is this, because of this term, and so on. So do it yourself and check that it is really a conformal transformation, that you will obtain something times G. I will put it to the offer to the next recitation, but just I will describe now that what is the problem. So this flow has as a generator which is conformal Killing vector. That means that this is the flow of conformal transformations in a standard Euclidean space. And now the important special case of conformal transformation, that let us have a look how conformal transformations of the Euclidean plane look like. It is an elementary computation, completely elementary, with a surprising result. You remember that when we started with Killing equations, I did the computation of Killing equations for the Euclidean plane, and we solved it, and we discovered that there are rotation around the origin and two translations. Now, because we did it already, I want to now to solve this equation for E2, yes, with x and y. So what we want to find is psi some a x y derivative with respect to x plus b x y derivative with respect to y. This unknown function is psi x, and this unknown function is psi y. So we have Lie derivative of psi g ij equals chi gij. Now gij is delta ij, and ij goes from 1 to 2. So remember that we already did it for chi equals 0. It was the equation for Killing for I equals 0. Now I will write down directly, do it yourself again, not for chi equals 0. Have a look to your copybook, and when we have 0 here, put there chi delta ij. Yes, so in x case chi. So in 1 case, here you will have just chi. For 2 case, you will have chi again, because G22 is 1. And for 2 case, it will be 0. Yes, add these two terms to your equations. And you will see that your equations look like that. That A x equals to chi half, and this also equals to by, and a y equals to minus bx. So I think that this comes from 1, 1 and 2, 2, and this comes from 1, 2 equation. For isometries, chi is 0, so we had two equations. A comma x is 0 and b comma y is 0. And from chi equals 0, we have a x is 0 and b y is 0. So a is a function of y and b is a function of x. And we put then it here and came to explicit solution, which was very simple. But now it is different, that you do not know what is chi. Chi is arbitrary function to be specified. So the important part of this equation is now that this equals to this. Yes, we don't know what is a comma x. It is some function chi which is unknown. And now have a look to this pair of equations. And do you know such pair of equations from some mathematics? Especially when you write x, y, you denote it as uxy, and b is v, then it is derivative with respect to x of u is minus y v, and here y of u is x on v. Do you know this pair of equations? You are from the third year. Did you have some mathematics number, I don't know what, 4, which is complex analysis? Cauchy-Riemann, exactly, yes. And we know that Cauchy-Riemann is an equation that if you have u x y plus I v x y, and it is an equation saying that this is analytic function. Or holomorphic. And what is important, that how many there are of holomorphic functions, how many there are solutions of this equation. For each holomorphic function, you have this pair of two real functions obeying Cauchy-Riemann equations. And there is infinite number. Yes. For example, Z2n is holomorphic. Yes, for any n, I mean at least positive. Yes, so for example, z to third power, you will obtain two functions, u and v, some combinations of x and y, which are polynomials, two polynomials which altogether give you fz, which is analytic, because this function is holomorphic. So you will obtain solutions. So the surprising fact is that the dimension of the space of conformal solutions here is infinite. You have infinite number . of linearly independent solutions, which is very non-typical. You know that conformal transformations are studied in the realm of complex analysis, typically. And more or less it is because of this fact that in terms of complex numbers, you can describe in the standard plane an infinite number of conformal transformations, that if you take any Zn for any n, for example, but a lot of other possibilities, you can produce a pair uv, and then what is the vector field? Psi is u derivative with respect to x plus v derivative with respect to y. For any uv obtained from some complex function, you have a conformal Killing vector. For some of them, you obtain isometry, because we know that isometries are inside. So maybe the question is, can you find a conformal Killing, some uv solution of these equations, which produces you isometry, not chi, so zero case here, and you can check, it is written in the hint of the exercise, that for some z to 0 and z to 1, you will find it that from this pair you also isometries. But from higher powers you obtain conformal transformations which are not isometries. Yes? So it is a very important exception from the rule that typically we will have just bigger Lie algebra for conformal Killings, but here you have very much bigger. Yes, the algebra, Lie algebra of isometries is 3-dimensional, and Lie algebra of conformal isometries is infinite dimensional. It is a big leap. Okay, then maybe the last note to this, I see that I will not start the next part, that have a look on this equation. It is psi k I g k j plus, well, first plus 3 dots, but here psi k g I j k, yes, plus this. This is the derivative of g. Here is derivative of components of psi. So in Killing equation, you have both derivatives of the unknown thing, which is psi, and the known thing, which is g. But you can have a look on this equation in different perspective, that you can have given psi and unknown g. The first point of view was that given g and unknown psi. But if you invert it like that, you see that for unknown g, you have also system of partial differential equations. Yes? Because there is a derivative of psi, of g also. So what is the meaning of this point of view? That sometimes you know you want to have some symmetries. You can describe these symmetries by some vector fields, that rotation is this vector field, translation this vector field, and so on. And then to try to find the most general G which has this symmetry. So we interpret this point of view that to find metric tensor with the prescribed symmetry. That symmetry is prescribed by several psi's, and we try to find the most general metric tensor with the prescribed set of symmetries. For example, in the plane, what is the metric tensor which is just rotation invariant, without translation invariance? Yes? So you will have several examples like that on the recitations, that, and the last thing, that it can be generalized to any tensor field some tensor field, like vector field, for example, that what is this, if this is given, like for this killing, so it says that we have given symmetries and try to find the most general tensor field with these given symmetries. For example, metric tensor or vector field or covector field or anything. Yes. So this kind of equations, similar to Killing equations, when regarded in this opposite way, is very useful for finding tensor fields with given or prescribed symmetries. I will give some exercises for recitation to find some interesting tensor fields. So, okay, thank you.